Welcome back to ECE 442-542. We're getting close to the end of the semester according to the noise level in the class. Everyone's anxious to finish up. Homework number 7 is due a week from Thursday on the 1st of May, so we are finishing up the semester. Homework 8, I don't know where we're at with that yet. We'll see. If you're in 542, you do have a project that is due on Saturday at 11:59 p.m. Our final exam is the first day of finals, but it's about the last time slot of that first day. It's at 6 o'clock to 8 o'clock. Hopefully they will have the doors unlocked, but now apparently there's only one door that's unlocked, so make sure and check both doors. We won't try to lock you out of the final exam. And teacher course evaluations, I'm telling the truth, I didn't intentionally spell that wrong. I think last time I said TEC online, and I didn't care that you filled it right out after giving your exams back, but I noticed the typo today. So it's TCE online. If you were saying teacher course evaluation, you would have found the right location anyway, or if you followed your link in your email. But all of that information is important to me, so please participate in the course evaluations. What I want to do today is finish up PID Control and get into the general Z-plane controller design approach, which really means how do you put zeros and poles down onto the complex Z-plane in an effective way with a strategy that allows you to shape the root locus so that all of the branches of the root locus are inside the unit circle at a given value of gain k. And I'm going to just remind ourselves of what we had last time with PID so that we're all on the same page. PID control, we looked at an example where we just used the first two, P and I, proportional and integral. The integral is for steady state accuracy. That gives us a type 1 system when we combine the controller C with the plant G. That type 1 system says that we have zero error due to a constant input. And we wanted to locate our dominant poles slightly inside the unit circle with a real part of 0.9 and an imaginary part of 0.1. And now we wanted to see, can we select the zero location, the value of beta, and the gain k to get us to those dominant pole locations. This is the picture of our system. Blue is the original plant. It was unstable. And our controller introduces a pole at z equal 1. And then we need to find, does a beta value exist that will stabilize or locate the dominant poles where those triangles are located. And this may not be a real accurate sketch, but it gives you the picture of what's going on. If we look at the expanded view, what we're wanting to do is actually design this location of the zero so that the closed loop pole does go through that triangle, and that means the root locus branch, the upper one, needs to go through that triangle. And I've tried to indicate where all of these angles are coming from when we start talking about branches going through certain points in the z-plane. That means the root locus needs to pass through that point. And if the root locus is passing through that point, then that point has to have an angle of minus 180 degrees. Which means that all of these poles and zeros need to algebraically combine, their angles need to algebraically combine to sum up to minus 180. And is that possible? And I simply start sort of justifying or explaining where some of this stuff is coming from. Our closed loop transfer function, that's what we're trying to achieve. And we want the denominator, or the closed loop dynamics, which are governed by the denominator of that closed loop transfer function, to be right on those triangles for a particular choice of gain k. That's the idea. And if this formula, 1 plus c of z d of z equal to 0, is what is determining our dominant poles, then that's where these two conditions come from. The magnitude condition, meaning if we took the magnitude of c and d, that's going to equal 1. If we looked at the angle of c and d, that angle has to be minus 180. Again, just reminding us of where the root locus is coming from and how we can use that root locus concept in a design process. So we're really saying if we want to pick beta properly, then we need all of these angles to algebraically sum to minus 180. The angle of our gain, k, we can basically not worry about if it's non-negative. It's going to have an angle of 0. Our angle of the 0 we're labeling as theta sub z, and we don't know what that is because we haven't yet specified beta. That's the only unknown in this equation, is this angle theta sub z. We have our angles of the zeros, and we only have one of those, so there's our theta sub z minus the angles of the poles, and that's just because the zeros are upstairs, the poles are downstairs. We subtract all the pole angles from all the numerator angles. That's where that expression is coming from. If we isolate theta sub z, that's the really only unknown we have in that expression, and we can now calculate theta p1 and theta p2 because theta p1 is determined by that pole at z equal 1. Theta sub p sub 2 is determined by the pole at z equal 2. And it's easier for me to think in terms of acute angles, and the calculator a lot of times just gives you an angle when you do an inverse tangent between plus and minus 90, and that's why I'm sort of keying in on subtracting these acute angles from 180 degrees to get me the actual angle theta p1 and theta p2. That's where that's coming from. And theta p2 is pretty close to 180 degrees because effectively it's quite far over in the right half or the positive portion of the z-plane. If we substitute in those numerical values for the pole angles, we end up with theta sub z being equal to 129, or basically 130 degrees. And what did we need? So when you're doing this design process, you might come up against a situation where it doesn't make sense or it's not working. And if that was the case, what would that theta sub z angle have been in this particular problem? What were we trying to make sure theta sub z was or was not in order to have an acceptable solution? And if we go back to the picture, and if you can superimpose a root locus diagram on these three singularities, what did we have to guarantee on this 0 as far as where it's located? And where it's located influences its angle. Right now, if we've calculated that angle to be 130 degrees, where is that open circle, that 0, relative to 0.9? Is it to the left of 0.9 as indicated in this sketch, or is it actually to the right of 0.9? If the angle theta sub z is 130 degrees, it's to the right, correct? It's 90 degrees, it would be right underneath the triangle. it's actually bigger than 90 degrees, meaning that 0, I don't know why I'm using body language, but the 0 now has to be to the right of 0.9. Does everybody see that or get that? And what we don't want, or what we didn't want, is for that angle to be larger than the angle contributed by theta P1, because then the 0 would have been between the two poles, and we never could have stabilized that system. Is that clear from your root locus knowledge? So if that triangle would have resulted in the angle of theta of z being bigger than 135 degrees, then we would say, whoops, we don't have a solution for those triangles. We need to change the location of those triangles. Those are not going to allow us to have a stable closed-loop system. Is that clear? And you might run into that. You might propose triangles somewhere that actually cause your system to be unstable. And then, or it may not be a valid solution. You might get a negative angle for theta sub z, and then you go, uh-oh, what happened? Then your constraints might be too much, meaning where you tried to request those triangles to live. Those triangles are desired locations. You maybe have the choice to move those around. And in this problem, we really didn't meet up with, or you weren't given any design constraints necessarily, other than you needed to stabilize the system. Is it clear the kind of thinking or processing you need to be doing for this design approach? This is just a PI controller. And what we have available to adjust is that 0 location. That's what we're adjusting. Here's now our corrected picture if we needed, and it's usually helpful to sketch what you have. You calculated an angle that's larger than 90 degrees. Maybe you need to draw that 0 in the appropriate location so that you don't sort of mislead yourself with the analysis. The sketch sometimes is helpful. Theta sub z we now just calculated to be 130 degrees. So that's a little bit smaller than 135. So it's not quite 2 z equal 1. We know it's a little bit to the left of z equal 1. And now I'm just, again, living with angles that live between plus and minus 90 degrees. I'm saying, okay, I want to play with theta sub z bar. I want to play with the acute angle. That's what my tangent likes to do if I'm playing with a calculator. Maybe play with angles between plus and minus 90. That's the only reason I'm defining a new angle. What in the world is he doing that for? Well, that's just to go back to high school and remember my trig, and I remembered that for these right triangles with acute angles. That's the reason I'm doing that. So now I've calculated this theta sub z bar based on what theta sub z was, which says that that angle now between the real line and that triangle location, the desired location, is 50 degrees. Whoops. And now I can use my trig. I know the tangent of that theta sub z bar is the vertical displacement, which is 1/10 of a unit, and I don't know how far or how close or how far to the right I am of 0.9, and that's my x bar value. X bar I can solve for. I do know theta sub z bar, and it ends up being 0.0833, and we did this last time. But I'm just going through it again because we're going to do it for another problem, and you'll see that these steps are similar, the thought process. We needed to add x bar to 0.9 to give us our beta. Beta is now 0.9833. That's pretty close to 1. And that's going to make for a pretty ugly overshoot behavior. Even though your triangles, if you just had a pure two-pole system, their overshoot is not too bad. Their zeta value looks pretty good if you can envision those logarithmic spirals that are inside the unit circle. We get K from the magnitude condition, which just means the controller times the plant, that magnitude needs to equal 1 at the triangle. And so we adjust K to get us to that point. We're cranking up the gain K to get us right to that triangle on the root locus. The root locus, we now know, passes through that triangle based on our phase angle condition. Now we need to adjust the gain K. And we can solve for K, plug in the 0.9 plus J.1, and we find that we have a magnitude of 1.2. There is now our controller. We now have our controller designed. And for this plant, which was unstable to begin with, yields those closed loop poles. And now I think what I am doing, since I know that you didn't believe me last time, let's look at the simulation. So here are some MATLAB commands. I enter the plant, 1 over z minus 1. You can look at this at your leisure. I know you're going to want to go home. Maybe you'll see a lecture at 7 o'clock tonight, but then after the lecture at 7 o'clock tonight, this is another lecture, not mine, but another talk at 7 o'clock, a technical talk about analog circuits, I believe. Yeah, that's the commercial. So we took a commercial break. Whoa, that's looking a lot of boxes. Then we put in the controller. We combine those. We form their product, the controller and the plant, and that gives us what I like to call a loop gain. That's what's in the loop. That's sort of the information in the loop, the transfer function of the product of the controller and the plant, C times G. And MATLAB has this nice feedback command that you can simply use. You have the forward transfer function, which I'm just calling loop gain, LG, and you have what the transfer function is in the feedback path, which I just want unity, but MATLAB is assuming you're having negative feedback, so you just have to put 1 in for unity negative output feedback with the feedback command. And just for the fun of it, I applied the pole function to that closed loop transfer function, and voila, I am meeting or going to where I said I would, 0.9 plus and minus J.1. Well, I might as well calculate the zeros. I know that that's where it is because that's where I located my 0. I said, oh, well, let's just keep using MATLAB functions, a DC gain, and it's a type 1 system. We would expect the DC gain as 1 for the closed loop system. And here is the step response. It does go where we want, but it kind of takes a big excursion to get there. We have a percent overshoot of 350%. But remember, this was an unstable system to begin with. Maybe it's okay that you go quite a ways away from where you want to eventually settle, and you do after 60 time steps. This is misleading in MATLAB. It forces, when you do the step, it forces a units of seconds, but these are just sample periods of 60 because I didn't specify the sample period. And we peak in 8 samples. I think that looks like about 8 sample periods, and we settle in 54 sample periods. That may or may not be acceptable, but that's the result of a PI controller. And now you need to go to whoever gave you this problem. Maybe you gave it to yourself and answer the question, is this acceptable? Is this behavior going to be okay? Can I live with this? And your system being unstable initially, maybe you're saying, this is fine. I can tolerate that much overshoot, because I eventually have zero error, or will have zero error. Well, I wouldn't have asked the question if I didn't want to answer it myself and say, let's try a PID controller. That's the whole point of this, right? Today's talk or material was supposed to be PID. We needed another consonant. So now we have a proportional integral derivative controller, which we will just go ahead and say that's going to be in this form. We won't worry so much about the P gain, the integral gain, and the derivative gain. We just want to place these two zero locations and the gain K in our system. It's the same plant. It's unstable, open loop, and we want to pick beta 1 and beta 2. Where do we put those? And let's just try something different. Let's try new closed loop or dominant pole locations. Let's say that we want to be at 0.8 plus and minus j.2. So that now here is our root locus diagram. And what have I done? I've drawn my triangles at roughly 0.8 plus, and if you were doing this, if you graphically wanted to design your controller graphically, you basically could, if you do an accurate job with your sketch. You could have your paper, and you can now accurately sketch and measure with your protractor and with your ruler and get these particular values determined. But what you don't know is where you're going to put those zeros. And to make the analysis simple, what I've done to start with is I've just said, let's try a simple solution and put both zeros right on top of each other. So I just have to calculate one angle for the zeros and include it twice. So this is a simple solution. Let me just say that. Let me say, now I'm going to assume a simple solution that is made up of two real equal zeros. Now, how do we solve the problem? How do we do the design? What do we already know? Do we know anything? And how do we approach the problem? Now we could pretend we're at a party, right? We're playing with, we've been playing with games with the root locus. Once we say root locus, we say, oh, we've got a game. We've got poles and zeros, X's and O's. Now let's make it a party. And the party game is pin the zeros on the Z-plane. Like pin the tail on the donkey, but now this is pin the zeros on the Z-plane. We need to figure, and we don't want to do this blind. We're engineers, right? We want to have a strategy, but we want to be able to locate those zeros where they need to be. And really what we're doing is we're sliding those around such that all of those angles algebraically will eventually sum to minus 180 if we want the root locus to go through that triangle. So again, we're using the phase angle condition to find this beta, which right now we're assuming both betas are right on top of each other. Beta 1 is equal to beta 2, and we'll just call it beta. Is that clear? We now need our phase angle condition again. Uh-oh. And we're going to do this with z delta equal to 0.8 plus and minus j 0.2. Now we have two zeros with the same angle, and we have a pole at the origin, so we have its angle. We have an angle due to the pole at z=1, and we have a pole at, or an angle due to the pole at z=2. The red poles and zeros correspond to our controller poles and zeros, and if we say PID, we immediately fix a pole at 1 and another pole at the origin. And what we have available to us are those zero locations. If we now compute those, theta p2 is calculated the same way as before. It's just now we're going up 2/10, and we're going over 1.2, and this ends up being 170 degrees, a little bit more than 170. Theta p1, by the way that I selected the triangle, I'm going up 0.2 and over 0.2, and that again ends up being 135 degrees. And theta sub p sub 0 is now looking from the origin to the triangle, and this one goes up 0.2 and over 0.8, and this one is 14 degrees. If I use those numbers, oh, and what did I forget? This needs to sum to minus 180. All of those angles, algebraically. That's our phase angle condition, and we're using everything known except for the angles of those zeros. So that now we have two of our zero angles, and that's now equal to minus 180 plus all of these pole angles. And if we do that algebra, we end up with 139.57 degrees. But that's two of the zero angles. So we're basically at 70 degrees for our angle now of our two zeros, 69.787 degrees. And I don't think you're going to be able to get that precision graphically, but you can get it analytically. 5 significant digits on your angle. But you won't be having to do that kind of analysis. Although this is in the z-plane, it does require that you are a little bit more careful with your significant digits than if you were in the s-plane, because now our stable region is just this unit circle. What's our picture look like? Whoops, maybe I didn't want to draw a vertical. Where are we relative to the triangle? If I sketch a triangle, where is beta? It's now to the left, isn't it? Since our angle is less than 90 degrees, if this is 0.8 and we're up at 0.2, we're over here somewhere, and let's just call this distance again x bar, and this is now theta sub z, where I now have two zeros at that on top of each other at the zero location. So that the tangent of theta sub z is now 0.2 over x bar, which allows us now to solve for x bar, and x bar ends up being 0.0736, 37. And according to this picture, beta plus x bar in this case is equal to 0.8, or beta now ends up being a little bit less than 0.8, or 0.72636. What's our controller? It's PID, so we know that. We have a pole at 1 and a pole at the origin. We haven't yet determined what our gain is, but we have now located both zeros on top of each other at 0.72636. Is that clear? And that choice of those two zeros will allow our root locus to pass through those triangles. Now what? Pardon? Now we have to find k, don't we? And how do we find k? And why are we finding k? We now need to fix those poles right at those triangles. We now know the root locus in general is going through those triangles because of the phase angle condition, but now we need to fix those right at the triangle. We're going to find k to place the closed loop poles at z delta equal to 0.8 plus j 0.2. And we can use our other condition, which is the magnitude condition, to make that happen. Where now we have k, z minus 0.72636. We've got two factors on top of each other. We can solve that for k. And this now has a slightly different structure. We now have the magnitude from the origin to that triangle because we have a PID controller, not just a PI controller. Downstairs we have these two factors, which means we only really have to compute that distance once and square it. And if we evaluate that at 0.8 plus j 0.2, we end up with 6.24678. That make anybody break out into a cold sweat? That k? Yes, no. Do we care? Or what is the range for k? Does it matter? It does. What's our root locus look like? What did we just, now we're saying that that gain will get us to those z delta values. So that our controller, C of z, is equal to 6.2, let's say 5, z minus 0.73 squared over z minus 1. We probably want to keep more significant digits when we're doing this, but I'm getting tired of writing. But that's in the ballpark. What we need to worry about, though, is now we have one more pole than we had with the PI controller. We had our plant having a pole there. And our controller now has 2 poles there. And we've now located our zeros right on top of each other. This is supposed to be 1, and this was 0.73, roughly. What's our root locus look like for this? What segments, real axis segments, belong to the root locus? That's a start, isn't it? We know this piece is on the root locus. What about between 0.73 and 1? Between 0 and 0.73? But this piece is on, right? So how many branches do I have? Root locus branches. 1, 2, 3, 4, 5, 6. I learned to count this morning, so I'm kind of wanting to keep using it. 3, right? We have 3 poles, we have 3 branches. The 2 poles to the right create 2 branches. They're going to break away, and then what happens? Do they go off? Where's the asymptotes? How many asymptotes do we have? 1, 2, 3, 4. How many asymptotes do I have? What's my pole zero excess? 1. So I have 1 asymptote, 1 0 at infinity, and we always know that's going off at minus 180. So those 2 branches between 1 and 2 are going to meet, break away, and what's going to happen? They are attracted to those finite zeros. And what do we know? We know that whatever happens, those are symmetric sketches, but we know that they are passing through 0.8 plus j.2, right? Plus or minus j.2. What we hope, or what we need to check, is whether or not, what do we need to check? And then I have you answer. We need to check where's the other triangle, right? Because we have 3 branches, we have 3 closed loop poles. We've figured out where 2 of them are by the choice of the gain k. We haven't yet verified where's the 3rd triangle. What would we like to have? If I said, oh, you can pick where that triangle is, where would you pick it to be so that you could quit playing with this problem? You don't have that choice, but if you had the choice, where would you place that 3rd triangle? Would it be between 1 and 2? No, you've already zipped around there, haven't you? You've broken away, and now you've come back. You're inside the unit circle. You're at those triangles. You are somewhere between 0 and minus infinity with that 3rd triangle, aren't you? That's the 3rd branch. You live somewhere on that 3rd branch. You would like for that choice of gain, which was huge, 6.2, I mean, it depends on the problem, but in this case, our PI controller gain was 1.2, wasn't it? Ugh. This one's now 6.5. Not quite, 6.25. That's maybe a little bit large. How can we check where the triangle is? Can we check? Do you have a way of checking somewhat easily? What would you do? We have this nice formula for k, don't we? How can we use that to check whether or not the third triangle is inside or outside the unit circle? We plug in z equal to -1 into this gain, and then what are we hoping? You hope that gain is greater than 6.25, right? And then your triangle would be inside the unit circle. So we're trying to find what's the gain to get us there. And then we're hoping that maybe that might have been bigger. So where would our other squares be? They would be closer to those zeros than the triangles, if that square was going to make our third triangle be inside the unit circle. So let's check our gain at the square. Is that clear where I'm wanting to check the gain? So that now if I plug this in, I had, that's hard, isn't it? I had the magnitude of z, magnitude of -1. Then I have the magnitude of z -1. Wow, this is getting a little bit more challenging. Being facetious. And what was the next one? Z -2. All over. And here's where you could use your dividers or your ruler if you don't have dividers. You could measure these distances. You now have -1 minus 0.7, whatever it was, 2636. I'm getting, and we had that twice, didn't we? And if we look at this, this is 1.72. That's almost the square root of 3, isn't it? If we were just looking at this real crudely, we would say, oh, I have 1, 2, and 3. Those aren't crude at all, are they? We know those magnitudes exactly, but the square root of 3 is 1.71, isn't it? Something like that. And this is 1.72. This is about the square root of 3 squared. So k is about 2 to get us to -1. Is that a good thing or a bad thing? We crank up the gain from 0, and we move along our root locus, and we get to a gain of 2, and we hit the square, which means that we might be there. Because when we crank up the gain to 6.25 is when we get to the triangle. We have now zipped outside the unit circle. We are now over here with our triangle. We don't need to know where the value, what the value is necessarily, but we know it's unstable. So that controller that we just designed is unstable. And that's what you need. That you need that attitude when you do it at home. You need to just kind of laugh. You need to just say, oh, bummer. Right? So this C of Z an unstable closed loop system. Is it clear why that's true? Is that making sense? We kind of went on an alarm when we saw that it was a 6.2. We go, oh, that's kind of big relative to what the PI gain was of 1.2. So then we needed to check our range of stability. We needed to understand what the root locus looked like, and then it was a simple case of saying, let's just evaluate the gain k at z equal to -1 and compare that value to the gain that caused us to get to the triangles. And unfortunately, that 2 is less than 6.25. So we have an unstable closed-loop system. Now what do? If we're playing a game, do we back up and punt? With this game analogy, do we just give up? That's not the attitude I want you to have. What do? Can we do anything? Are we stuck? So we need to change the locations of the zeros, which will do what? Will that change anything? Pardon? It'll change the numerator, won't it? What are we trying to do? We're trying to probably, well, we want to be a little less aggressive maybe with our choice of triangle. Where do you think we should put those? Pardon? On the root locus. Yeah, we need to put them on the root locus. That's where they will be on the root locus based on our design, right? We'll design it so that they are on it. And these were on the root locus, weren't they? These triangles. Darn things, though, they gave us an unstable closed-loop system because we had to crank up the gain more than we wanted to get to the triangles. So that's meaning maybe that 0.8 plus and minus J2 is not where we want it to be. Where should we go? This is why you're getting paid the big bucks after a class, after, well, yeah. Maybe now. Any suggestions? Any ideas? Okay, do you want to know what I tried? I said the PI worked. Why don't I just try those triangles? 0.9 plus and minus J.1. Maybe not such a good idea, but that's what I tried. It worked for the PI, didn't it? But remember, the PID, we've introduced a second pole, haven't we? And we have a second zero. We have one more branch than what we had with the PI controller. And so that makes things a little bit more challenging. Let me just say, since what if we tried that? And again, maybe we kept the zeros equal. All right, I won't bore you with the steps. You know how to do it, right? It's exactly what we did before. But now, if you follow through that, you end up with a C of Z equaling, are you ready to laugh again? 12.17 Z minus 0.8597 squared, because I kept them on top of each other. Can you guess what happens with that controller? Ooh, didn't work. That's even, the reason that's not working is we're trying to really bend that root locus over quickly from the point z equal 1, and we're starting with two branches. That are between z equal 1 and z equal 2. So that didn't work. All right, help me out here. What do we do now? besides just sit and laugh. We could do that for a while, and then we'd start crying because our homework's due. What do we do now? What have we tried? Well, maybe we need to think a little bit more open-minded than what I was allowing. We had our unstable pole there, and we said we wanted to do a PID controller because we maybe weren't happy with 350% overshoot, and now we can't seem to stabilize this silly thing with a PID controller, and we thought it'd be better. So now what do we do? Well, if we do a PID controller, we're forced there, but what if I don't force the zeros to be on top of each other? Real and equal. Maybe I let them be real but unequal. If that's the case, where would I locate these zeros? If I say, give me two real unequal zeros, general location that might help or that might work. Do you have an idea where we would put those? Do you have an idea where we wouldn't put them? Where would the zeros not belong? I feel like I'm at Sesame Street. One of these things is not like the other. Is that still playing? I don't know. One of these things just doesn't belong. Where do the zeros not belong? What can we not do with zeros? Cancel unstable poles. So we know that we can't put one on top of two. We can't put one on top of one, and we need to stay away from 1 to 2 in general, right? We can't put our zeros there because then we would be stuck with a branch or two living outside the unit circle. So we have to avoid that segment between 1 and 2 with our zeros. And what are we trying to do with those zeros? Come here, come here. We're trying to pull those poles into the unit circle, aren't we? Here, little boy. Or whatever it is, some kind of an animal. Right? Come here. So we're trying to put something there in the z-plane to attract those poles inside the unit circle. You know what I did? I was getting frustrated. Can you believe that? Don't get me too frustrated. I said, you know what if I do this? What if I just put them there? Is that going to work? What's the root locus look like now? If I gave you this on the final exam and said, sketch the root locus, could you? And we only started with one pole, and we introduced a controller that sprinkled 2 poles and 2 zeros. And now I say, sketch the root locus. What's the root locus look like? Do I have any branches or anything between 2 and infinity? How about between 1 and 2? How about between 0.9 and 1? Between 0.1 and 0.9? Between 0 and then minus infinity. Oops, I skipped over. Between 0.1 and 0. No, because I have 4, don't I, to the right. What's my pole zero excess? How many infinite zeros do I have? So the only thing going off to infinity is going off at minus 180. These two are going to approach each other and then break away and come over here, aren't they? And one's going to go to that finite zero and another's going to go to that finite zero. Should I do this in MATLAB? Because now, what did I say? I said I was getting frustrated, didn't I? Yes or no? So I just started doing the following. Why don't I, whoops, I really got frustrated. GD, that's my discrete plant, is 1 and 1 minus 2. And I didn't have a sample period selected, so I just say minus 1 for the sample period. There's my plant. Then I'm going to say, okay, here is my third controller design. It's going to be a transfer function, and I don't know what the gain is. So I'm going to find that with MATLAB. So I'm not going to put in a gain, I'm just going to put in a 0. And I already know where those are. I'm going to combine, so I'm going to convolve two first-order polynomials. One of those polynomials is at 0.1, and the other one is at 0.9. And again, whoops, you guys need to wake me up. That's now my numerator. Better be. Now I need to put my denominator down, and my denominator, I'm not going to convolve that. That was z squared minus z plus 0, isn't it? And I don't know what my sample period is. There's my controller. And if I was questioning what that was, I could say, well, where are the poles of CD3? 0 and 1, that's what I wanted. And my 0, or zeros, of the controller are at 0.9 and 0.1. Is it clear that I have what I wanted? Now I need to combine those two, my plant and controller, and sketch the root locus for that combination. So I'm going to multiply those two pieces together to get my loop gain. I now have a loop gain, which is CD3 times GD. There's my root locus. Oh, it gets really pretty, doesn't it? Red and green and blue. So we have three branches, don't we? We have a green branch, a red branch, and a blue branch. Pretty tree, isn't it? The green branch we can kind of imagine. The red branch maybe, no, blue, but it's a root locus, isn't it? It's roots anyway of a tree, maybe. All right, now what do we do? Now I forgot what I did. So now we need to click on it to see if we can find a gain. What I do, can you just click on it? So now I just left mouse clicked on that, and I see that I have a gain of 1.76 and a pole at 0.75 plus j I 0.75. And that's pretty close to what I clicked before. Okay, so now I know my gain. What I can do is I can change my loop gain by that amount, 1.76. Meaning I can now go back into I'm just going to increase my gain on my controller by 1.7. Actually, that was closer to what I ended up clicking. And that combination, I'm just going to say LG, the new LG, Thinking now of an appliance. I need to do laundry, I guess, tonight, so I have an LG. Sorry. 1.7, let's say, for the gain, times LG. All I did was introduce a magnitude change in the numerator of my controller, which gets multiplied by my gain. Now what do I do? Now I need to close the loop on that, so now let me do a closed loop transfer function for the third time and say that's feedback of LG, I hope that's what I called it, with that. And now I can say poll CLTF3, and what am I hoping happens? Yay! Why did I say that? Why did I say yay? Well, maybe I don't know. Maybe that's still making me nervous. 0.76 and 0.26. I could say absolute of answer. Am I justified in my relief? Well, maybe. At least I've stabilized the silly thing, haven't I? Because all my polls have a magnitude less than 1. What's the ultimate test? I better hope that this crazy controlled system has less overshoot than 350%, right? Oh, I haven't already created a figure, have I? I did earlier today, but that's long gone, so I was going to do a new figure window, but I don't need to do that. Oh, I do need to do a new figure window because I just sketched the root locus. Oh well. That's now my plot. And it's not quite as bad, is it? Instead of going up to 4.5, I'm just going up to 2.5. Yes? So if I wanted to, I could right-click and say, oh, show me the characteristics. I could look at the peak response, and then I could go over here and say, oh, what's my overshoot? So now my overshoot is 152% instead of 350%. Maybe that's better. And I am still settling at 1. Yes? So now the question was, if we had not requested, I think this is the question, in the PI controller, we requested closed loop poll Z deltas at 0.9 plus or minus J.1. The question I think now is, what if we had instead made our Z delta 0.76, whatever this was, plus and minus J.26? Is that the question? The answer is I don't know. We would have to try it. It may not have quite the overshoot because I think this one wouldn't be as demanding because you're not trying to squeeze it down towards the real axis as quickly and as abruptly as you were with 0.9 plus and minus J.1. Now you're maybe being more gradual with bending that over. And the other thing is maybe your 0 would slide a little bit to the left of Z equal 1. It was almost right on top of Z equal 1 at 0.983. If we can move that a little bit more to the left, that would help our percent overshoot. And that might happen with this bigger arc that's coming around to place our poles at 0.76 plus and minus J.26, if that makes sense. But I would have to simulate it, or you can simulate it. You can go home tonight and check that out. Maybe that will be homework 7B. Question? How did I pick those 0 locations at 0.1 and 0.9? Out of thin air. But it was a reasonable guess, right? Because I knew, that's why I was asking you guys. Now I can't even remember where I was. I was dancing here. and you missed that at home. What was the question? Oh, how did I pick 0.1 and 0.9? I knew they needed to be between 0 and 1, didn't I? And it wasn't working really when I had them together. So I said, I ended up with them at 0.7. Is that me? Class over? Ooh. No, but I'm about out of juice. So I said, let me just try sort of an extreme case. I said, it didn't work together at 0.7 on top of each other. Let me separate those. And I just said, you know what, I'm getting tired. Let me just put them at 0.1 and 0.9. And probably if I would squeeze those together and make this one not 0.9, but maybe 0.7, and the other one maybe leaving it at 0.1, my percent overshoot would probably improve. But I need to be careful that I don't go zipping with that third branch outside the unit circle when I crank up the gain. And you could check that differently than the way I checked it if you were doing it with your calculator. You could evaluate the gain at z equal to -1 and see if it's bigger than the 1.7 or the 1.76. Other questions? Yes? The question was, is this a PID? Are you trying to stump me or what? Oh, so the question, I think, is really trying to confuse me, but the zeros are not directly related to the gains on your three different terms. They are a mix of the three different terms. You have a p term, an integral term, and a derivative term, and those are not directly related to the zero locations. They're all three sort of mixed up. Meaning, in our parameterized controller, wherever that was, wow, right there, these beta 1 and beta 2 are some way related to the integral gain, the derivative gain, and the proportional gain, but it's not directly coupled. So you would have to, once you've created or designed a beta 1 and a beta 2 and a k, then you would have to go back to the previous lecture and say, okay, how did the integral time, the derivative time, and the gain come into those three coefficients? You do have three parameters, and you would have to, if you had somebody giving you a PID controller that had three knobs, a proportional knob, an integral knob, and a derivative knob, you would want to back those gain values out of this final design. Meaning you would have to equate the numerators and figure out where is the integral gain relative to the betas and the k's. The k should be the proportional gain, so you know how to pick that. But then the beta 1 and beta 2 you would have to relate to the sample period and to the integral time and the derivative time, and we're skipping over that process. We didn't explicitly go through that. But you're right, you do now have three different adjustments. They're just not exactly connected with the three adjustments that we now have parameterized here. Our three adjustments are k, beta 1, and beta 2. In the real world, you'd have to translate those into the three knobs on your PID controller. Does that make sense? Other questions on this design that I can attempt to answer? Now what do we want to do? Well, this was so fun, sprinkling poles and zeros on the z-plane, that we can do that in general. Now, what I'm saying is, what if we now, instead of forcing ourselves to have a PID structure, what if we simply said, and maybe we even make it bigger than that. Maybe we make a fifth order. We have 5 terms in the denominator. Maybe we make it third order. We have 3 terms in the denominator and maybe 3 in the numerator. But now we have 5 parameters to play with. To force this into a PID structure, we would set alpha 1 to 0 and alpha 2 to 1. And then we have our PID controller. But now we could say, let's just leave it like this. For example, what if somebody gave you this problem? And this could be a homework or a final exam problem. What if they said, here's g of z, and it's 2 z minus 1 over z minus 1 half z minus 2. And they leave you alone and they say, design a controller, C of z, to stabilize this system. Is it clear that this system is not open loop stable? What's the pole zero diagram look like for this? I see a pole at 2, don't I? I see another pole at 1 half, and where's my 0? At 1. If I used a constant gain controller in a unity output feedback configuration, what's the root locus of this look like? What's my pole zero excess? 1. So how many zeros at infinity do I have? 1. And where are my where are my real axis segments that belong to the root locus? Did everybody get that? Can I ever stabilize that system with a constant gain controller? It's not going to happen, is it? I'm always going to have a pole between 2 and 1 if I just used a constant gain controller. So now what do I do? How do I pick a C of z? Any ideas? What are some observations? What do I know I can't do? I can cancel. What can I cancel? I can cancel if things are inside the unit circle, can't I? I just can't cancel poles or zeros that are on the unit circle or outside the unit circle. So I can't cancel that 0 at 1, and I can't cancel that pole at 2. I better not be sprinkling poles and zeros to cancel poles and zeros outside the unit circle or on the perimeter. But that doesn't mean I can't introduce unstable poles and or zeros. Because what's happening with this guy? With just a gain, I have a segment locked between 2 and 1. I need to somehow get rid of that segment. How do I get rid of that segment between 2 and 1? I need to put a pole over here to the right of z equal 1, don't I? Maybe to clean up my analysis, I would say, or to make it easy, I would just put a pole right there. I don't have to. I could put it somewhere between 1 and plus infinity, but I don't want to put it too far. But this way, if I calculate something at 2, I just have to double it. Don't have to do any extra calculations. But what's the root locus? Oh, What's the root locus look like now? What's my pole zero excess now of the controlled system? 2, right? Where are my zeros? How many zeros at infinity do I have? 2. And where are they going to live? At what angles? (180) divided by the pole zero excess, right? So now I have asymptotes at 90 and 270. The fundamental one's at 180 divided by 2, the pole zero excess. It's at 90, and the other one's, and where is the asymptote centroid going to be? Well, I add up my poles and subtract my zeros. It's actually going to be maybe there. And what's going to happen? Oh. Ooh. Ow. Keep laughing, because this isn't working, is it? So what do we need to do? Or what can we do? That was good to put that pole there, but we may have to add a 0. Whoops. So I want you to go home and convince yourself that maybe we started here. Maybe what we can do is put a pole there, and let's just cancel that. Now what's the root locus look like? What happens when I cancel a pole and 0 inside the unit circle? Is that okay? Now, effectively, you can just virtually erase that, because it's canceled. Now what's the root locus look like if we virtually erase this? 2 poles to the right of a 0. And these are right on top of each other. Get out that compass that I just bought and draw a circle. Right? It's what you're doing. You're drawing a circle. And you know the radius of that circle. It's not even hard to calculate, is it? Boy, I can't even control my enthusiasm. Oh, that was supposed to be a circle. Because now we brought the pole zero excess back to 1. And maybe we just pick a gain to put us right there where they both combine. We're right at the origin. Our response will be a deadbeat response. We'll pick up at that point on Monday. But I think you have material enough to do the homework. And there's an announcement, although